I hope you had some time to make your own experiments, have CoCoALib compiling and tried, and everything works. And now we do some more exciting things. So we start from this function. This is also the code that you can already find in X minus NF normal form example. And so the this function is the function reducing is what we called normal remainder LPB. And this is how it is called in that example. So it computes the normal remainder of a polynomial f with respect to a vector of ring LMs V, and the result is a ring LM. Now we see in this line I wrote const sparse polyring P instead of ring, and I will explain you in a bit why I had to specify it as a sparse polyring. And another thing I want to tell you is this function owner, which corresponds to the function ring of that we have used in CoCoA 5. So we create a ring element which lives in P, and we create another ring element R, which is the remainder, which at the beginning is F. Then the first thing we want to do is to find the reducer of R respect to V, and this is the long a number J. And while we had the repeat in our CoCoA 5 function, and so while the result is different from -1, the impossible value, then what did we do? We had the definition of M as the leading monomial of R divided by the leading monomial of VI. We have a problem here. One problem is that we do not have the LM function in CoCoALib. Why don't we have LM function in CoCoALib? Because it's not very useful. Because that would mean that you have to create an object which is probably a waste of some time. You probably want to work with the LPP or with the leading coefficient. So we decided not to for the time being. Might be that we change our mind. And I want to show you a side of CoCoALib if you want to do very optimized things. In fact, there is a function which actually creates creates the result of this division in a very optimized way. So we don't even need to know the whole polynomial. It just looks at those bits. It's we have this double way of looking at things in CoCoALib. One which is very straightforward, very clean syntax, which does all the checks, very robust. And then there is this kind of syntax, which depends on the ring you do the operation. And when you make explicit the name of the polynomial ring, and then you just go at the raw pointers. This makes no checks whatsoever, but that means that when you do something like in a Grosvenor basis, you do many checks. You might want to use these functions because you already know that you are inside the correct environment, and you can avoid looking every time is the ring and the ring of these three elements are all compatible. If you are inside the Grosvenor basis computation everything is the same ring and you don't want to do these checks all the times. So keep that in mind. It is very dangerous. You shouldn't do it in your very first version of the code, but only when you want really, when you want speed in the second version, not in the first version of the code. So I create this, I had this, I make you notice, this is the ring element I had at the beginning, and it is a ring element in P, so it is in the correct ring. So I can use the row pointer because I know it is in the correct ring. And then I have this, which is an element of P. I can multiply it by Vj. And then I do what in Cocoa 5 was R gets, R minus this product, which in C++ is just called with this very compact syntax when I want just to change the value of R, subtracting the result of this multiplication. This is C and C++. Then at this point, if the remainder is 0, then returns the 0 polynomial, or I could say return R. And if it is not 0, look for the new reducer and go on with the loop. At the end, when you get out of this loop, then it means that R is no longer the leading monomial of R is no longer reducible, so just return R. If you want, you can compare this with what we did in Cocoa 5. We use the repeat. Here we use a while. We had the return inside of the loop. Here we have it outside of the loop. It's fine. I thought of making them identical, but then I decided not to, so that you see two ways of writing essentially the same logic in the code. Having done that, this is what was an exercise for you in that lecture, was to write the actual function doing the normal remainder also for the tail. So we will see here how it is done. We can do it in CoCoALib. So if the polynomial is 0, return the polynomial itself. Then make the call P the ring of F. This is the point. Usually I can just write ring instead of specifying it is a sparse polyring. But if I want to do tricks like this one, I have to specify that that is a sparse polyring. So this is another trick like the one we did here. And so I want to, I need to be more precise in what kind of ring it is. And then we have the final value, the answer of the normal remainder, which is a polynomial in P, and the temporary remainder, which at the beginning is the polynomial F. So how is this done? So at the beginning, we compute the normal remainder of F respect to V, and we assign it to the temporary result. If the temporary result is not 0, then I take the leading monomial of the temporary value, the temporary remainder, and I move it at the end in the back of the polynomial answer. I'm showing you some very dodgy code inside, but I want to give you all the feeling of what you can have inside CoCoALib. So this takes the leading monomial from one polynomial and moves it in the tail of the final answer result. And then we recompute in the temporary value the normal remainder of the temporary value without its head. respect to v. And we do it until the temporary value is 0. And so what we had collected in this step, in the answer value, is really the complete remainder, the full the remainder of the full division of the polynomial f by the list of polynomials in V. And so we return the value as an R. Again, this function, like the function before, takes a const ref ring lm and takes a const vector ampersand. This means by reference, and that means that we do not copy the value of this list of polynomials. We don't want to make copies. So we pass it by reference, but we insist it is constant. It is not, we are sure it is constant. It is not going to be changed by this function, even though it is called by reference. We don't have these kind of problems in COCOA 5, because in COCOA 5 we have reference counting. It is a very nice way of doing things hidden by the user, so that it doesn't make a copy unless it needs to do it. So if you don't do it you don't need to have this const reference in COCOA 5, is because reference counting works well in COCOA 5. So now we have these two functions, and then I copied, these is my program. I copied from xnf.c the part that it is in the program. So I create a vector made of these two polynomials. Then you see I create the ideal. This is the syntax, which is pretty similar to the syntax in COCOA 5. So I create an ideal with this vector. I can print the generators of this vector. I show you some of the functions in COCOALib. This is the list of generators of an ideal. This is the computes the Gröbner basis of the ideal, and the result is again a vector of ring lm. And so I can print this Gröbner basis. And this is a comment to say that there is a general function which is called tidygens, which works for any ideal in COCOALib. In the case of polynomial ring, tidygens are a Gröbner basis. So then I create a polynomial. I print it out. I compute the normal remainder with respect to the generators. I compute the normal remainder with respect to the Gröbner basis. And I check that indeed in COCOA the function nf of f, y, I is the normal form of f and I is the normal remainder of f with respect to its Gröbner basis. Then there is another example here. Here I want to show you that if I really want to write operations, then here I use the trick of writing the polynomial, the string that represents that polynomial. But suppose that I want to construct a polynomial doing something, so that the way of doing so is that I take in x, in the variable x, the index of p. So p had 3 indeterminates, which were called x, y, and z, but those are the names of the indeterminates. COCOALib doesn't really know the names of the indeterminates. Well, COCOA 5 looks at the names of the indeterminates. Here it is more abstract. This function actually works in COCOA 5 as well. So I call x the indeterminates, then x is a vector. So x0, x1, x2 are the first, the second, and the third indeterminate in P, which are x, y, z in their names as strings, x, y, and z. So I can create another polynomial, which is g0 plus x0 times g1. I print it out, and again I compute the normal remainder respect to the generators and the Grobner basis. Okay, so I compile it, make. Okay, there is an error here, of course, because so we show how to read the errors. As always, you look only at the very first error, because the other ones might come from a cascading of the problem before. So look at the first one, line 106, which is here. Here I define this polynomial f. Indeed, in the example before, we already had defined f. So the problem here is that I declared f to be a new thing, and it isn't. I already have f, so I can just do this. So f is already a variable in my program. It is a ring element. This is fine for me. I just redefine f with this value. I hope I don't know. The other is h. Okay, so now I go on. Let's see if I got some other errors. Of course. Okay, so there's an extra closing brace at line 123. So you see what kind of errors you get. Okay, seems that I have one too many. Okay. That might be a bit embarrassing to have this in a video which will be public, but I think it is interesting, especially when you start, not to get scared when you get errors, because that's very common. X, my G basis, and here it is. So this was the first part that we did in the previous two videos. These are the new. This is the new idea generated by this vector. And this is the Grobner basis, which is another vector of two elements, which are not the same as before. This is the comment about tidy gens that I said before. This is the polynomial, the new polynomial f, and this is the remainder respect to the generators, and this is the remainder respect to the Grobner basis, which is the normal form of f respect to the ideal I. And this is the polynomial h, which was a combination of G1. Here it is. It is a combination of the two generators, so it belongs to the ideal generated by G1 and G0 and G1 in this case. But the normal remainder respect to the generators is now 0, and with respect to the Grobner basis is 0. So when the normal remainder respect to the Grobner basis, that is, the normal form of f respect to I is 0, if and only if the polynomial belongs to the ideal I. Let's stop for a bit and then get ready for implementing the Grobner basis algorithm.